So, welcome back to our lecture of the 6th week. I think this is the second lecture, but we are going to speak about what is called improper integrals. Improper integrals are a very important class of integrals, because here we will speak about integrating over unbounded intervals. Whenever we have spoken about integral of a to integral from a to b f(x) dx, a and b is a closed and bounded interval, which is not true, and we ask ourselves that what is the meaning of this question. Now, for example, I can ask you, is there any meaning to this question of area under a curve from the area under the curve point of view? It might look very strange, because for example, I am talking about an integral of this form. So, here so you look at this parabola. So, here is 1, this is 1. So, yeah, this is alright. So, this is 1 1, this point. Now, we are trying to understand whether this area makes sense. So, you might be saying, oh come on, this area is going continuously towards infinite, how can you have a finite area? So, does this has any meaning or not? So, here is 1 and it goes towards infinity. So, but I can say, okay, let me think about a little bit more slightly different problem. Of course, I am not putting x equal to 0, then this function has no meaning. So, this function would look slightly different. Then starting from 1, this is 1 1, this is point 1 1. So, does this area has a meaning? Here it does not look that you will really have a finite area, here it might be that you will have a finite area. But you might say, oh no, however hard you try, this 1 by x square will continue to come nearer and nearer to x axis, but it would never go and touch the x axis. So, how can I say area would be finite? Okay. So, let us try to define this integral within the limits of what we know. So, if we want to do that, we only know about finite stuff. So, maybe it is not a bad idea, you can try it out, that you take the following definition. So, what you do, and this is what approximation is all about, some sort of when you think of that, okay, immediately you say, okay, I know about the bounded stuff. So, I will say, okay, let me try a to m f(x) dx, where m is some finite number, and then I keep on increasing the value of m. The more I increase the value of m, so if I take m, this integral is not equal to this integral, because here I have a finite area. Area might or might not have a finite area. So, as I keep on making the m bigger, I come more near and near to the value of the integral if there is some value. So, we define this integral to be in this following as limit m tends to infinity a to integral a to m f(x) dx. So, you calculate for every m and then find the limit. If this limit exists, then that particular value would be called the value of the improper integral. Okay. So, let us have this two tests, one for 1 to infinity, 1 by x dx, and another is 1 to infinity, 1 by x squared dx. So, let us first for this case compute Let us look into an integral of this form 1 to m 1 by x dx, and then so this integral would be nothing but logarithm of m or ln m, the natural logarithm log to base e actually, minus log e of 1, and log e of 1 is 0. So, basically this, if I at all have to define, then this should mean this, and you can say, oh come on guy, you just draw the graph of log. The graph of the log function is like this, at 1 it is 0 and then it keeps on growing up and up and up and up. So, what is in there? So, what have you done there? So, you are showing that this is actually plus infinity, the limit finitely does not exist. So, this integral does not give us an area, the area under this function when the limits are unbounded, one of the limits is unbounded one side, does not give me a finite area, which looks quite natural by the diagram. So, we say that this thing diverges, this integral diverges. This is a technical term, you may not be so worried about this technical term that this is diverging and this is doing that. So, let us try out this integral. This might be quite new to anybody who has been just out of high school, because in high school you do not learn all these things. So, here we are obviously doing things very differently. So, you need to look into that aspect. Now, what is the issue at hand is the following. So, let me do the same calculation here. So, I take an integral 1 to m 1 by x square dx, which is integral 1 to m x to the power minus 2 dx, which going by our standard formulas x minus 2 plus 1 minus 2 plus 1 1 to m. So, it is, so this is nothing but what? This is nothing but, so first you put, so this becomes x to, this becomes minus 1, this becomes minus 1. So, basically it becomes minus 1 by x 1 to m. So, essentially this is now becoming 1 minus 1 by m. So, what is the limit? Now, if I want to define, let me, limit of 1 minus 1 by m, this limit as m tends to infinity, what is that? So, that limit is 1, because as m goes bigger and bigger, this goes to 0, and because m is going to infinity from the right side. So, this goes to 0, while we have 1 here which is free of m. So, that is the limit. So, it is amazing. So, we are essentially telling you that in some limiting sense, in quotes, in some limiting sense, the area under the curve 1 by x square area under the curve f x equal to 1 by x square actually, right, area under the curve f x equal to x 1 by x square actually gives us an area from 1 to infinity. You want to calculate the area under the curve, it has an area and which is 1. You cannot say it has an area in the sense of the area that we know, but an area in the limiting sense. So, you have to understand here, this simply means area in the limiting sense. you must understand that you might not always have this a to infinity kind of thing, right. So, you need not always have this kind of thing. So, how would you show that an integral is convergent, means finite. So, if you have say one integral a to infinity fx dx, how are you going to show that it is finite? One of the good ideas is the following, that suppose f is such that over that range fx is less than equal to gx, then you know that integral a to m for any m fx dx is less than equal to integral a to m gx dx. Okay. So, once that is done, what is the aim? The aim is the following. Now, you take the limit on both sides, provided the limit exists. Suppose the limit exists here, this is finite, that this are convergent. So, this integral is actually called a convergent integral. Then a to m fx dx is less than equal to limit m tends to infinity a to m gx dx then what's happened? What happens here? If this is finite, say this is finite, so this is strictly less than infinity. So, then limit of integral a to m fx dx is less as m tends to infinity is also strictly less than infinity. So, this is a finite quantity and hence it is also convergent. Let us see, let me see if there is any way to show that any such function where we can do such a thing. So, let us now show you an example of how we can actually use what we have just discussed. For example, if you take the integral sin x by x square and you want to integrate it from 1 to infinity. See, this is not an easy integral. I do not think this is an elementary integral, in the sense that I do not think there is a function whose derivative would be this thing. It is not so easy. So, when you have here we had functions which has an indefinite integral, this function, but here I do not think you have an indefinite integral. It looks quite complicated to me. So, what you do, maybe there is, maybe I can't just figure it out immediately, but the look makes me feel it does not. So, what happens is the following, that here you now look into the fact that sin of x is always less than equal to 1. It does not matter, it is always less than equal to 1. It is less than equal to 1 by x square. So, 1 to infinity sin x by x dx, x square dx is less than equal to 1 to infinity 1 by x square dx. Of course, I am just writing, I have just skipped the limit part there separate, because I know that this limit exists, this is 1. So, what we can say that this integral is less than equal to 1 and hence it is a finite valued stuff. So, now please understand that no area cannot be, you cannot have an area integral, if you take an area under an integral, it cannot be minus infinity. So, such things do not happen. So, please be careful about that. You might ask a question, okay, it might be minus infinity, still it is less than 1. But no, there is nothing called minus infinity, because you are computing the area. You can compute a small area from 1 to m also. So, basically you cannot have, if you draw the graph of sin x by x square, you will immediately realize that you cannot, even if you take a little chunk, you cannot have and you will have an area under the curve, but you will not have a area which is minus infinity. There cannot be negative areas. So, areas are any always greater than or equal to 0. So, not greater than or equal to 0 in the sense that if I take the modulus of sin x, for example, if I take the modulus of sin x, then we are talking about non-negative functions. So, we are talking about areas. So, this is always greater than or equal to 0. As mod of sin x is always less than 1, the same story will go through. So, this is one way of doing. Of course, the thing could be minus infinity to a, and you can write down the same stuff and you do not really have to bother. I would like to say that okay, there is a very important concept here, it is called absolute convergence. What is the meaning of this absolute convergence? You know this f is less than or equal to mod of f, f of x for any x. So, if we integrate out say from a to m f x dx, so for any proper integral it will be assume that it is integrable. So, see all these functions f that you assume they are Riemann integrable in over an interval. Now, here it would be So, now if this integral is finite, means this one once I take the limit, if this integral becomes finite, then we say that the original problem is also convergent and the original problem is also finite. So, if you take the limit of a to m, m tends to infinity, so there are functions which are convergent and but not absolutely convergent. So, if this is finite, so if this is strictly less than plus infinity, this part, then f would also be finite, and hence, so when this happens, so whenever I can integrate, I can get the improper integral of mod of f x, then I will immediately show that integral of mod of f will also exist, and hence it will be, what is that? It is then we call that the integral f, the integral f is actually absolutely integral a to b, a to infinity f x dx is an absolutely convergent integral. So, here is an example, you can simply take this example. For example, your sin x by x square is less than or equal to mod sin x by x square. So, in fact, if you look at it, the sin x is also bounded by minus 1 by x square. So, if you integrate it a to infinity, if we integrate it a to infinity dx. So, this is anyway you have just proved to be less than 1, and here I can again integrate this side also a to infinity dx, here we will immediately prove that it will be minus 1. So, the integral here is lying between 1 to infinity, So, 1 to infinity sin x by x square dx is lying between plus 1 and minus 1. So, this integral is called absolutely convergent. So, this whole integral is actually called not a to infinity. Suppose if this exists, so if integral a to infinity mod f x dx exists, then integral a to infinity f x dx is called absolutely convergent. So, this is one aspect of it. Now, you know, you can have things in slightly different way. Your integral could be very strange. Integral could be within a closed and bounded interval, but at one of the points or some point in between in the integration range, the function blows up or is not properly defined. In that case, what would be, how would you define this improper integral? So, for example, let me take this example from the book by Samuel Goldberg on real analysis. I do not think that you really have to bother much about the book, because this is anyway a very common example of such situations, that if you have a situation like 0 to 1, 1 by root x dx. Of course, root x is differentiable and it is defined at 0, but 1 by root x is not. So, it will become a meaningless thing if 1 by 0 if you are looking at the left boundary, lower boundary. But in between, 1 by root x is absolutely properly defined. So, how do you handle this situation? So, again we have to bring in that simple idea that, okay, let me try one thing. I increase the value of epsilon, because I know that within 0 to 1 except 0 for all other points the function is well defined. So, if I take some epsilon positive and then I try to evaluate this, and naturally I would expect that if this limit as epsilon goes to 0 from the positive side, 0 plus this limit exists, then I would be able to call that limit value as a value of this integral. So, here everything is done in the sense of a limit. You see, the whole of calculus is essentially based on the concept of limits. So, that is something you have to get into your mind very, very clearly. All these things, whether derivative, integrals, are all names given to special kind of limits. So, limit epsilon tends to 0, epsilon to 1, x to the power minus half dx. I am actually doing the computation. So, limit epsilon tends to 0. So, it is epsilon to no. So, it is x to the power minus half plus 1 by minus half plus 1. So, it is limit epsilon tends to 0, it is from epsilon to 1. So, you will have here x to the power half root x, 2 root x, right. So, 2 root x epsilon to 1. So, limit epsilon tends to 0, 2 minus 2 into root epsilon. So, as epsilon tends to 0, the answer is 2. So, you see, you can give a finite number to it and we call 2 as the value of this integral, right. Now, this is always not the case that for such situations where you do not have this infinity business, there is a bounded interval, you will immediately come and hit into nice things. For example, if you take look at, let me just check the example from Goldberg. It is, for example, this integral x minus 1 square, I should be x minus 1 square. So, if you look at this integral 1 to 3, 1 by x minus 1 whole square. What about this? That x equal to 1, the thing does not work. So, whether this is a convergent integral or divergent integral, means whether this exists or it does not exist. So, whether these are the finite value or these do not have a finite value. So, that is something we have to look into. So, this I can leave as a homework and tell you this one does not have a finite value. So, there are certain issues, for example, there are certain integrals which are convergent but not absolutely convergent. That is, their modulus is not convergent, but the integrals themselves are actually finite. Such integrals are called conditionally convergent, but we will not discuss about them at all here, right. This is not the situation where we need to discuss them. So, sometimes the limit can be on the opposite side. For example, where you have on the upper part there is a problem on the upper end, not on the lower end. Now, what about this integral? So, you understand at x equal to 1 it blows up. So, the idea possibly would be to first calculate out 0 to 1 minus epsilon and then compute the limit of this. So, if this limit is finite, then of course now here epsilon comes from 0 minus, because here you have 0 1 and you have dropped by an amount epsilon, because you know between 0 and epsilon the function is well defined. So, 1 minus epsilon has to go to 0, 1 minus epsilon has to go to 1. So, epsilon approaches 1 from the right side actually. So epsilon approaches 0 from right from. So, you are taking a positive quantity of right epsilon goes to 0 plus right sorry. So, 1 minus epsilon so 1 minus, when that is epsilon goes to 1 from the negative side. So, you can also write epsilon going to 1 minus right. So, basically we have to compute this integral, but it is not so easy to compute this integral, that I can assure you. Why? Because you need to know that always it is not possible. This is a kind of integral which comes up often in physics in the study of vibrations. For example, pendulum motion, these are called elliptic integrals, and it is not so easy to compute them. So, what we can do is to first show that it is absolutely convergent. Basically what we do is that we look into this. First I would ask you to check whether this is correct. Is this correct? Is this correct? Not correct? When x is lying between 0 and 1, this is not correct. Why do you think so? Because I can write this thing as 1 by root over 1 plus x into 1 minus x. So, it is equal to 1 by root over 1 plus x into root over 1 minus x, but this is a quantity bigger than 1. So, its root is also bigger than 1. So, 1 by that is a fraction. So, it is fraction of this quantity, and hence this is less than 1 by 1 minus x. Now, if I can now evaluate this integral from 0 to 1 to infinity and then do something, then you get the result. So, I just ask you to show that from 0 to 1 or 0 to 1 minus epsilon 1 by root 1 minus x dx is actually 2 minus 2 root epsilon. Let us check this calculation out, and then if you take epsilon limit goes to 0, limit as epsilon goes to 0. So, what are you going to get? This will become 2. So, essentially you know now that 0 to 1, because we can now you can integrate both sides and take the limit on both sides. 1 by root over 1 minus x square dx is less than equal to half or less than equal to 2. So, it is a finite integral, it does converge. Of course, this is naturally bigger than 0, this is a non-negative function, so this is bigger than 0. So, you put the bound, so it is finite. So, there are some other issues which we will discuss in the next class and give you some interesting examples like gamma function and beta function, which are part of this discourse on integrals, because they are very important class of integrals which arise in physics, in engineering, repeatedly in statistics, for example, gamma function plays a major role. So, we would look into some such functions, and also we will tell you how to compute some integral using some these sort of integrals using heuristic techniques. But for the time being, we are pretty fine with this basic idea. So, we will start with some basic idea tomorrow called the Cauchy principal value in the next class, and then we will go to talk about gamma integrals and beta integrals, some interesting class of integrals and some nice formulas I will write down for you just for you to have fun. But I hope you have an overall understanding of what we had tried to explain today. Thank you very much.